Sorry, I got a bit late setting this up. But yeah, so last week, we still have some unfinished business from last week, discussing Buchanan's algorithm. So the first part of the lecture would cover that. And then I'll jump onto the new topic for week 5. So last week we were talking about Buchanan's algorithm. So it's an algorithm to construct suffix arrays. And just to give a maybe a 1 or 2 minute recap, it had, if you have a string 1 to n, it had this iterative process of working in phases. And in each phase, you're handling the processing of the prefix 1 to I. So every phase deals with the prefix 1 to I. And what do you do in that processing in every phase? You build an implicit suffix tree containing all suffixes 1 to I, meaning that the implicit suffix tree after phase I will contain all the information of the suffixes 1 to I, 2 to I, 3 to I, all the way to I to I. Now then, when going into the next phase, I'm sorry, there was a problem with my mic. Going into the next phase, what do you do? You take each of the suffixes 1 to I and extend by 1 character, I plus 1. There's 2 to I extended by 1 character, I plus 1. 3 to I extended by 1 character, I plus 1. The last suffix in the previous phase was I to I. That gets extended by 1 more character. So you have 2 characters for that thing. And then in the current phase, you introduce a new character, I plus 1. Is everyone clear about what the general theme is? And then what did we discuss? We said that doing this extension, so if you're extending some suffix j, starting at j, ending at I by the character I plus 1, we said 3 possible rules happen. What are the rules? Can somebody, does somebody remember what the rules are? What is rule 1? Was an extension at the leaf, isn't it? So the path j to I goes all the way to the leaf in the previous state of the implicit suffix tree. So when you're extending by character I plus 1, you're just increasing the label on the edge to the leaf by 1 character, incrementing. So it previously ended at I, now it's going to end at I plus 1. So that's the leaf extension. Then we had rule 2. Rule 2 was you had a scenario where the path j to I ended in between. So going from the root, it ended in between an edge. Okay? So 2 things could happen. You either could break that edge, create a new node, and hang the new letter that's coming at I plus 1 off it. Okay? That's rule 2. And the rule to alternate was that you didn't have to break the edge because you could directly hang the leaf off an existing internal node. So rule to alternate. And then the last rule was rule 3, where j to I was there. Obviously, you're extending the implicit suffix tree I. But when you looked at I plus 1, you've seen the pattern before. So it's the best rule that can ever happen. You do nothing in that case. So rule 1, you have to do something to the edge going into the leaf. Rule 2, you have to do some surgery about either putting a leaf on or breaking an edge and put a new internal node and hanging, stuff like that. But rule 3, everything is easy. And then we talked about how the processing of Buchanan works, what the rules were. We also said what this shortcutting, instead of going all the way from the root, you did something called suffix links, where suffix links basically say that if you have a path from the root to some internal node. I'm just giving you a recap. None of this it was not explained in the previous lecture. I'm just giving you a recap so that we can have a context of the discussion in the first half. So if you have a path so if you're doing a suffix extension j of phase I, so that means that you're adding the I plus 1th character, you would have to do the extension, either rule 1, rule 2, rule 3, you would have, if you did nothing else, you would have to travel from the root all the way, go looking for which rule I have to apply, right? So you have to say, is it rule 1 or rule 2 or rule 3? So you start at J and go try and find out where the end I is, and wherever the end I is, you say, well, okay, what's the next character? Does it trigger a rule 1, rule 2, or rule 3? One of those, that's the agenda. So when you keep descending down, traversing, hopping from the root to the next internal node and next internal node, depending on the structure, you get to a point where you're standing on an existing internal node, okay? And then that, you do some surgery, rule 1, rule 2, rule 3, underneath that existing internal node. So a new internal node to be created under, okay? Wherever you're standing is an existing internal node. In the worst case, or in perhaps the best case or worst case, depending on how you want to see it, in one case, you don't ever go down the tree because there's nothing else beyond a leaf to a root. So you're starting at the root, there's no other internal node, so you're standing at the root. Or you could go hop down the internal nodes until you come to a point where to do an extension I plus 1, I'm standing on an existing internal node that's not been created now. That's just you're saying, and they said, is it rule 1 or rule 2 or rule 3? And if it's rule 1, there's nothing, so you basically do a rule 1 extension. If it's rule 2, you have to have to create a new internal node. You don't descend down, you just create standing there, do the surgery, hang off the new internal node. And then if it's rule 3, do nothing, right? So wherever you are standing, so that is an internal node that has a path, some j. So think about, I'm just giving you an example here. I mean, this is not pertaining to the slide is not pertaining to the discussion, but this is a good example where if you have a root, you keep coming down. So technically, you're doing a jth extension in general. So j plus 1, j plus 2, although it says 1, 2, 3 because it's pointing to something else. So j plus 1, j plus 2. So this is an existing internal node where at least the figure shows that you're doing a rule 1 extension. So this is an existing internal node. We call that existing internal, the deepest existing internal node in every extension as the active node. Why is it called active? Because that's where the activity is. Do I apply rule 1, rule 2, rule 3 from that thing? Now, so when you're standing there, it's a path j to k minus 1. That means at a suffix link, there exists another internal node v. There's another internal node v, which has a path from the root to v, which is exactly the same path except the first character. So if it's j plus 1, j plus 2, all the way to k minus 1, the path from the root would be j plus 1, j plus 2, j plus 3, all the way to k minus 1. Does that make sense? So that we talked about the suffix link. So if you have nothing else, so what we're going to do now is see if you had nothing else to beyond the idea of what an implicit suffix tree is, and you're doing incremental updates to implicit suffix tree from I to I plus 1 by adding one letter and some shortcuts. What would you do? Okay, what would you do if with this algorithm? Although in the next part, I'll show you that there are a bunch of tricks that you use where you never have to start the suffix extension from all the time from the suffix 1. So although we are starting from suffix 1 for every phase, so if your phase I, 1 to I, 2 to I, 3 to I, extended by I plus 1, we'll go through the drill of what would happen if you had nothing, no tricks, this is what you would do, but then later on I'll say, well, you could do something much more clever, and that's where the linear time speed up happens. Okay, that's where it happens very quickly. So I've already told you what an active node is, remember that. So it is not a new node that you've created. If you applied rule 2 in the current extension, you're never standing on a new node. You're standing, your control is, well, if you are standing at an internal node, it has a child, and if you're creating a new node, you know the child, you are creating a new internal node, and you do the pointer arithmetic to make sure that you insert a new node by breaking the edge. But your control is always on an existing internal node, so that's the active node. Now, what is remainder? Remainder is a string, a substring. When you're here, your idea is to go down from some suffix extension j all the way to end of I. But when you're standing on an internal node, you might still have some more of the path left. Okay, so j to I, but you went only up to k minus 1. So what's remaining is k plus 1, k plus 2, all the way to I. And then because you're standing on an existing internal node, the remainder could be of size 0, 1, 2, 3, 4, so on. If k minus 1 was I, then there's no remainder, right? If k minus 1 was I minus 1, you have one more remainder to go. Or depending on whatever the remainder is, it's a substring of a certain size. So would you remember what an active node and a remainder is? With those definitions in mind, this is what you would do if you had nothing else, no tricks to play. So every phase I plus 1, it's extending I, the implicit suffix tree I by one letter. So my claim is that so the suffix extension 1 to I extended by I plus 1 will always be a rule 1 extension. Why? Because rule 1 will happen if you have not seen that pattern before. Okay, you have never seen that pattern before. So 1 to I is the longest possible thing. There's nothing before. Okay, so when you say I plus 1, it has to be at the end. Okay, it's always going to be a rule 1 extension. So you come to some point where you start from the root, traverse, you come to a certain internal node. In one case, the internal node could be the root, depending on the structure of the tree. But it could be you traverse down from the root to that internal node, existing internal node, and apply rule 1. And then what? Well, because it's an existing internal node, last time I told you that whenever you create a new internal node, you have to worry about creating a suffix link. An existing internal node already has a suffix link. So, and we talked about how to create a new internal node at the end of last lecture. I'm not going to repeat that, but know that that active node, does it have a suffix link already? Is it a new node? It's not, isn't it? It's already been there. That means that whenever it was created, its suffix links got resolved, so it will have a suffix link out of it, right? So in the next extension, rather than go from the top from the root, you just, because you're standing there, your control is there, you just surf the suffix link that it's pointing to. Now, U is pointing to V. So if V is there, now remember what's the path from R to U? It was because of its suffix extension 1, 1, 2, 3, 4, all the way to some k minus 1. That means that the path from R to V is 2, 3, 4, 5, all the way to k minus 1. Which means that you have saved that amount of effort of traversal, or at least in the worst case, you've saved that amount of effort in traversal. Yeah? Does that make sense? All right. So if you were there, now what are we doing in extension 2? We want to find the end of the suffix 2 all the way to I and extended by I plus 1. Isn't that what the goal is for in phase I plus 1, suffix extension 2? I want to find where the path 2, 3, 4 ends in I plus 1 so that I can add one more letter using one of the rules. But then I got a shortcut, I got a free ride until k minus 1. So 2 to k minus 1 is covered because I just took a shortcut from U to V. Does it make sense? Because that's the definition of a suffix link. Which means that what is remaining is k plus 1, k plus 2, which is what we call the remainder, isn't it? We call the remainder. All that needs to be done now is once you transfer control from U to V, you have to do the traversal as you would have done if you were starting from the root, except that now you're doing a traversal just on the remainder because you already covered k minus 2 to k minus 1. Does that make sense? Now you can see that this process will let you go down 0 or more nodes down V because it all depends on the structure of the tree. So you can imagine that you've gone from U to V, surf the suffix link, and then from that point you're going down 0 or more internal nodes. Why did I say 0 or more? Because an edge directly connected to V could have the remainder somewhere there. So you're applying whatever rule right there. But at some point, you're repeating the process that you were doing where you're traversing down. Now, would that give you a new notion of an active node for extension 2? When you're traversing down, what did we say the active node was? Active node was, in any traversal, it's the deepest existing internal node where you're doing rule 1, rule 2, rule 3. So the whole idea is every extension is doing applying these rules. So if you go from V along the remainder, you arrive at a new definition of an active node. And then you would say which rule you have to apply. Okay? So if you have done 2, can you do 3? A suffix extension 3? Well, wherever you are standing, that is your new active node U for extension, suffix extension J equals 2. So it traverses from U to V, its partner, it will have some remainder, because once you're going down, you know how much you have traversed. So you start with a remainder in 1, that remainder get potentially chopped off, it'll have some more remainder, and you keep moving forward. You can see that as you're going from 1 to 2, 2 to 3, 3 to 4, and then at some point, you will have to stop that, you've finished your phase, okay? Now, when you finish the phase, what happens to the active node going into the next phase? Well, the next phase is essentially, you see what I'm trying to say? If you had nothing else to do, you would have to essentially start all the way from the root again, and it will create J equals 1, J equals 2, just like the scenario. You're going to create the whole process again if you didn't have anything smart. And if you'd implemented what we have discussed, it will run worst case n cubed. Okay? It's still n cubed with the shortcuts. Okay? It seems as if we have saved one thing, but it's very hard to gain this. So whatever I've told you here, I've covered in general. So the general procedure is whatever I told you, you are in some phase I plus 1 of extension J. You have your active node, you have your remainder, you do your operation, go to the next J plus 1 extension of phase I plus 1, and then go down, traverse, keep doing this traversal just as you saw how you went from 1 to 2, you keep going from 2 to 3, 3 to 4, 4 to 5, all the way until the end. There's nothing smart here beyond repeating that idea in text, okay? And we already answered this question in the last lecture. What about the suffix links for newly created? Does anybody remember what happens when you create a so if you have an active node, and on the edge of the active node, you have applied rule 2 regular. That's the only way you create a new internal node is through rule 2 regular. What happens? How do you resolve it? In jth extension of phase, let's say I, you create a new internal node. The idea was that in the next phase, the very next phase, you're either going to create a new internal node or you're going to find an existing internal node which you can connect the new one that you created just now. So you can resolve it in the next extension. So every time you are doing this process, your active node is an old one and it already has been, its suffix link already exists. So you don't have to get into a scenario, what happens if my active node is new? Well, no, it can't be new because by definition it's an existing internal node. And it's been resolved whenever it was created. And if you did the creation, and the only part that will trouble you in your sort of implementation, at least the main part that will trouble you, would be how do I resolve the suffix links, right? Now, with this background, something magical will happen now. How do you go from n cubed to n in one fell swoop? And there are going to be 4 tricks. They are really easy tricks. Some of them are straightforward, like the one we are seeing, but some of them require some more thinking. Okay, Arun says something. What did he say? You go and say, go to your labs and tutors. Then your tutors would say something. What did they say? And you kind of some process of assimilation. You will say, aha, I kind of get it now. Okay, so hang in there. So what are the tricks? The first trick is obvious. Now, first trick is something that you know already from 2004. You never store explicit substrings on the edge. The label of an edge is start point and end point. I mean, I think you would have done it as start point and length in your in 2004, depending on how it was taught. But whether you have a start point or length or start point and end point, they are interchangeable, isn't it? If you know start point, end point, you know the length. If you know start point and length, you know the end point. Okay? So you're essentially not storing a substring on the edges. You're storing two numbers, start point and end point. So when you look at 2, 8, if you look at the string 2, 8, ABB, AABB would be ABB, AABB. I'm writing it in that order in which you're traversing from the root down. Okay? I'm writing it in that way, down order. Okay? BB, AABB would be 3, 8. So 3, 8 would point to BB, AA, BB. So every time you do this, the first trick is be space efficient. You're always storing two numbers. Now remember, those numbers need not point to your specific. So if you're doing extension J of phase I, so J, J plus 1, J plus 2, you're going for that. The numbers J, J plus 1, J plus 2 is specific to an extension. Okay? But then the paths that get created, the edges that get created would have been in the previous iteration, so it might be pointing to the previous instance of the substring that you had observed. So when you say these numbers, you're saying that is the characters that we are traversing, are they similar? You only need to store one instance of it. Okay? You will see that when you implement it anyway. So trick one is easy. It's something that you've already done, is my claim. Okay? You don't have to store the labels explicitly, but you have to store it as start point and end point. Okay? Trick two, it looks too much of text, but I'll explain. It's very, very easy. It's in fact intuitive. Okay? You are doing some suffix extension. You have an active node. I already told you what an active node is. It's the deepest existing internal node under which you are applying your rules. Okay? Every extension would have an active node. Okay? It's either the root or something down. It's going to be an internal node. It can never by the way, an active node is never a leaf. Okay? Because so once you don't have to go to the leaf at all. Because if you go to the parent of a leaf and then you are saying, is it rule 2 or rule 1 or rule 3? Rule 1, rule 2, rule 3. One of the three things have to be applied. You just don't go down anymore because you can stop. So existing internal node is an active node. And you have this remainder. So you have covered j to ik minus 1. The remainder is k to I. Whatever the rule you're applying here, rule 1, rule 2, rule 3. The next extension, I told you, you go from U to V, surf, and you have to cover one or more, 0 or more internal nodes that traverses along the remainder substring. So what's the remainder here? Let's look at the remainder here. Z, A, B, C, D, E, F, G, H, Y. I mean, I just came up with some example. Okay, what's remaining is that you have covered everything in the previous extension, all the way from J to K minus 1. At K, you had Z. At K plus 1, you had A. So, by the way, these numbers, there would be a start point, end point out here. So, it is some number of letters from the start point that's remaining, right? So, you know which phase is it, you know which extension you are doing, you're keeping track of that information, and you know how much you have covered, okay? So what is remaining is whatever you have to cover to find the end. The remainder is Z, A, B, C, D, E, F, G, H, Y. You transfer control from U to V. Now I have to traverse in the direction of that remainder string to come to the end I, so that I can do the I plus 1th extension of the next phase, of the next extension. So we have finished J, you're doing J plus 1th extension. So you kind of transfer control. So the skip count is very important. You are not comparing every letter. You are here, there would be only one edge in the direction of J. there's only going to be one edge in the direction of z. What's the first letter of the remainder? Z, right? There's going to be one edge in the direction of z. You don't have to compare what's the next letter, so on. Why? Because you know that j plus 1 to I already exists. If j plus 1 to I already exists, then all I have to do is be confident that if there is a path in the direction of j, it will take me to whatever path that whatever the internal node it's pointing me to. So I can directly say that out here there's a edge coming in the direction of z. If I skip from that internal node to the next internal node, how many characters do I skip? In this example, 2, isn't it? How long is my remainder? 10. So I'm still didn't reach the end, so I can skip. So I've skipped from V to B, to this internal node, not B, this internal node that my mouse is pointing to, okay? I've skipped 2 internal nodes. Now, what's the remaining after I've skipped? It's B, C, D, E, F, G, H, Y. That's the remaining string. So at this node, internal node, I say, if I went in the direction of B, because I've already skipped the 2, I don't have to compare these letters, you only compare one letter at each time. So if I go in the direction of B, how many characters do I skip? Well, it turns out again, it's 2 characters out here. So previously I've skipped 2, now I've skipped 2, so that's 4 characters that I would skip in total. What's the length? Length was previously, reminder's length was basically 10, wasn't it? Have I crossed the end? No, I have not yet crossed the end. So skip. Well, I can skip from that internal node to that internal node. So which means that I have, in principle, on the remainder, I've covered the first 4 letters. Now I have to go in the direction of D. So that's letter 5 in the remainder. So if I went in the direction of D, I have how many? So start point, end point tells you how many letters there are. And you say, well, if I go in the direction of D, there are 3 letters. Previously I've covered 4, now I've covered 7. 4 plus 3 is 7. So 2 plus 2 plus 3 is what I'm going to skip. If I went in that direction, I've still not got to the end of my remainder, so I'm going to skip all the first 7 letters. So going from here to here is equivalent to skipping 7 letters on the remainder starting from V. Yeah? And then now I'm coming here. Let's say that there were more. So if out here there is G, H, Y, let's say that there were 4 other letters on that edge already. Once I come to that internal node, I have to go in the direction of G. But if I went in the direction of G, I would shoot past the end that I'm interested in, because there are more letters than what the remainder allows me to. If I shoot past, what did I say? Go to the deepest internal node under whose edge you're applying rule 1, rule 2, rule 3, which means that your new active node becomes the one that I've highlighted in green. That becomes your new active node. And that's where you apply rule 1, rule 2, rule 3. Okay? And now it's like back to square one, isn't it? So now this becomes the U of the current iteration. So this was the U of the previous iteration, and it had some remainder. Right here, the remainder here is G, H, Y. That's the remainder. Going into the next suffix extension, you're going from U to its V, and then you're going to traverse down G, H, Y now, because you've already covered everything else. You're only going forward on the string. Does it make sense? So that's the skip count trick. Perhaps this will be rule 3 and rule 4 are perhaps where the entire magic happens. So what did I say? First trick was space saving trick. Second trick was essentially saying that when you're traversing, don't compare every character. You have to just compare the first character going out and skip count it. So you're skipping internal nodes. So when you skip from one internal node to another internal node, you're jumping over a bunch of characters that define the start point, end point, and that tells you how many, you're counting how many do I skip, and the count is based on what's the length of the remainder. So 2 plus 2 plus 3 have not yet covered the remainder, but let's say after 2 plus 2 plus 3 you're at 7. Well, the moment you have 2 plus 2 plus 3 plus 7, that's more than 10. That was the length of the remainder in the previous line. Yeah? So then you kind of stop. That's your deepest internal node under which you're going to apply rule 1, rule 2, rule 3. Now, this is where be attentive. It's an easy rule, but you'll have to be attentive for this. So this is, I will turn camera on. I've not yet started writing anything on the whiteboard, so don't worry for those who are doing this stream. So one, let's call it, so we are doing phase I plus 1. That means you've finished phase I and you're adding one new character, let's call the character Z, at position I plus 1. Are you happy with this? Okay. If at some position, I'll call the position POS, if rule 3 was applied, okay, maybe I'll draw a longer start point so that if rule 3 was applied at that position, that is what if the extension at that position, suffix extension starting at that position, so j to I extended to I plus 1 was rule 3. What does it mean when it's a rule 3? Anybody? Come on. Let's make it interactive, otherwise it's a monologue. Yes?
Okay, so that's the pattern before stuff.
Okay, you've seen this pattern before. Okay, we see this pattern that appeared before. That means that j to I was there also followed by I plus 1. I've observed that before. That's what rule 3 is. Okay? So I'll just change this to a smaller. So you've seen if it's position rule 3, you've seen alpha at least once before, and the next character was Z. You've seen that before. Okay? That's what rule 3 means. Okay, now if at position plus 1, would you have seen the pattern position plus 1 to I followed by Z? If you've seen all the letters from position to I followed by Z, the question is, would you have seen the pattern position I plus 1 to I, so position plus 1 to I followed by the next letter? Would you have seen that? So if this is beta and that was C beta, so alpha is C beta, you would have seen C beta followed by a Z again, isn't it? Okay? Now, would you have seen the pattern position plus 2 to I before? So position of 2 all the way to I plus 1, would you have seen that? Would you agree that every single pattern contained within this alpha followed by a Z would have to have been observed before? So if you observe rule 3, would you also, is it clear to you that it's always going to be a rule 3? The first time you see a rule 3 in a certain phase, everything afterwards would be a rule 3? Is anybody unclear about that suggestion? Anyone wants me to repeat that? So the first time you see a rule 3, I will rub this off and get back to my original state. because I need a bigger, so that's I, that's Z. So if I saw, I'm just going to mark some position where rule 3 happened, rule 3, okay? My claim is every other position all the way to I will have to be rule 3. Now question is, what happens to I plus 1? Will I plus 1 be any other rule? Because remember, in every phase you have an extra suffix that you have to account for. What's the extra suffix? It's the single character suffix that is coming in. So we can prove that if you have seen alpha before, this is the alpha. If you ignore the first letter, you would have seen, ignore the first, because the whole alpha was seen. If I look at any suffix of alpha, I would have seen it before. Now question is, what happens to this new suffix here in the phase 1? Which can it be any other rule other than rule 3? So when you have I plus 1 to I plus 1, that's the suffix. String I plus 1 to I plus 1 is nothing but a single letter Z. So your active node would be root, because because only one letter, it will have to be the root. Would you have seen Z before? You have seen alpha followed by Z before, that means you would have seen Z before. So it would be rule 3. So all of this, in fact, all of this has to be rule 3, if the first time you see a rule 3. So what did we say rule 3 was? It's the best rule we can have. It's do nothing rule. So in any phase, the first time you see, in any phase, doing extension, the first time you see a rule 3, you stop the show. Stop a rule. That's the rule that we are trying to talk about. Okay? So whenever you see, so this is phase I plus 1, finished phase I and phase I plus 1. So by the way, what was position again? The first time I saw rule 3, correct? So what happened to all these positions? What rule applied until there? Maybe I'll change the color. What rule applied? The first time I saw rule 3, I stopped. What would be the rules before? There are only 3 rules. It would have to be rule 1 or rule 2, isn't it? Because the first time I saw rule 3, that was rule 3, I stopped. Okay? You finished at extension at that position, you realize it was rule 3, you stop. You never saw rule 3 before. If you saw rule 3 before, you would have stopped earlier. Okay? That means that everything from here to here, before that position, is rule 1 or rule 2, correct? Okay. We will give a special name to that position. We call that last JI. It's a last position before you saw a rule 3. That means that last JI plus 1 would be that position. That's where you saw a rule 3. The last time you saw a rule 1 or rule 2, okay, last last position, you saw rule 1 or rule 2 in some extension I. Because we can call this phase I, we can call this I minus 1, we can call this I. It doesn't really matter what the labels are, whether you're doing phase. If it's phase I plus 1, it will be last J I plus 1. If it's phase I, it will be last J I. If it's phase I plus 2, it will be last J I plus 2. Right. And you only need that that variable. You don't have to keep track of them in the previous phases. You only need the one that you have just finished. Okay? Now, this is where all the magic happens. Okay? So, trick 4, the last trick really, is once a leaf, always a leaf observation, right? Now, what does it mean? Do we ever do anything that destroys a leaf, deletes a leaf? We only create new leaves, either hanging off an existing internal node or create a new internal node and hang off it. So where does a leaf get created? Rule 2, isn't it? Either rule 2 alternate, which creates a leaf from and hanging off the existing internal node, or rule 2 regular, where you're creating a new internal node and hanging off a leaf. So when you did that, so when you did, when you actually created, so there are two scenarios. So you could have a tree. So you could, that's a new leaf that you created using alternate, rule 2 alternate, and that would be the character that you're extending, and you call that j. It's starting at, so you're doing some extension j, so j plus 1, all the way out here. You could not go any further without actually branching the path towards z. So this is basically the last letter. So whenever you create a rule 2, you will have one letter there, right? Whenever a leaf, rule 1 is, so this is rule 2 alternate, a leaf has been created, you get one letter out there, okay? Now another option, another possibility, I'm going to write it here. So that's going to be, so that's a state. I mean, you could have multiple paths. Now you have to break this edge, create a new internal node. That's another option. So that's rule 2 alternate. That is rule 2 regular. Okay? See what I'm trying to say here? Now, when a leaf gets created, there's nothing more you do. If it's rule 3, after that, it's either going to be rule 3 or what. Every time you see a leaf, there's the edge attached to that leaf, edge leading to a leaf, is only going to be a subject to further rules, right? So the leaf never disappears away. So once a leaf, always a leaf. You don't have to really worry about anything. The leaf always exists once you create it in rule 2, okay? Okay, and we sort of explain that in that context. Okay, then what? Okay, we'll just basically, I'm just going to come down here because the key point that I'm going to make is the picture out here. So we said everything in any phase, we'll consider phase I, which means that I minus 1 is going to I. Okay, it doesn't matter whether it is I going to I plus 1 or I minus 1 going to I. So we have a scenario where in any phase, let's call it I, last ji will be telling you the last time you've applied rule 1 or rule 2, correct? Isn't that clear? So last time you've done rule 1 or rule 2. Now can I ask you, if, let's take one instance, let's take that point here. So let's call that j prime. We saw a rule 1. So what does rule 1 at this point mean? That j prime to I minus 1 extended by a letter was a leaf extension. That means that traversing j prime to I minus 1, you added a letter that became a leaf extension. Correct? That's what rule 1 means. So what happens, okay, listen to this question very carefully. What happens in the next phase, not next extension, next phase? So that's 1, j prime, whatever was in the previous phase, this was I, and then in the next phase, this is phase I plus 1, there is some letter here at I plus 1 that is extended. Let's call this letter X. Doesn't matter, okay, what we call that letter. If this, in phase I, j prime to I minus 1 extended by a letter was rule 1, what rule would be j prime to I extended by I plus 1? So can you see that this was, what are the previous states? So this was Z previously, and there was a new letter here. So extending it was rule 1, what would be this rule? So what do you do? I mean, if you knew nothing else, what do you do in phase I plus 1 for extension j prime? You try to find the end, isn't it? End of the previous phase. Where was the end of the previous phase? I. When you add a letter, doesn't it have to be rule 1 again? If it was rule 1, this has to be rule 1. Think about it, okay? This is something that requires you to think a bit more, okay? I've already explained why, but you need to digest that information. So if you saw the end, so in every phase you're trying to find the end extended by one letter. Previously you extended it at a leaf, which means that if you find an end and extend it again, it'll have to be at the leaf. There's nothing beyond that. Now here's the catch. So we said this region is either rule 1 or rule 2. Okay? It can't be rule 3. I've already said that whenever you saw a rule 1 in this region, you would see a rule 1 again in the next phase. Now what happens if you saw a rule 2 instead of a rule 1? What rule would that be? Anybody? Let's take a regular case. The idea would be the same. This is a new one. Sorry, I changed the color scheme. So that's a new one that I've created. Maybe I'll just be consistent, not to confuse. So root. So you're going to create a new internal node. Let's j prime. This would be j prime, and that would be z. That would be a scenario when you create a new leaf in rule 2. Okay? Rule 2 alternate also similar scenario, except that this will be to an existing internal node. But the key point is there will be a leaf called j prime and a letter called z hung off it. Now, if it was rule 2 in the previous one, what rule would it be in the next phase? So I know j prime to z. So j prime to z, what rule would it be now? What rule would it be? Anybody? Come on. Could it be rule 2? Could it be rule 3? Could it be rule 1? Anybody wants to give a try? Rule 1. It has to be rule 1. So the reason is that you've just created a single edge leaf that leads in the direction of that leads in the direction of z. The next letter, x, has to be the last letter, so it has to be rule 1. So the point is that if you kept track of last ji, 1 to last ji are rule 1 or rule 2. So this entire region was rule 1 or rule 2 in the previous phase. All these become rule 1 in the next phase. They're all leaf extensions. Now, which means that if I find a constant time method to do all leaf extensions between 1 to last ji, if I change the phase from I to I plus 1, what if there is a method that allows me to, because I know that 1 to last ji is going to be rule 1 or rule 2, was rule 1 to rule 2 in phase I. Going from I to I plus 1, without doing any work, I should be able to finish all my rule 1s in constant time. All this should be free. This area, free, or rather constant effort. How do I do that? We will see in a bit. Okay, keep that in mind. So if it were free, that means that going from I to I plus 1, that part's done. The moment I change from I to I plus 1, I have finished that part. So where do I pick up the extension? Instead of starting from 1, where do I pick up the extensions from? I pick up my extensions from whatever the position where I first saw rule 3, which is 1 after that position. Okay? Now, at that position, you could get certain rules again. So whatever some rules, there are some constraints which your labs, your tutorial will explore. It doesn't matter, at least for the initial thinking, that let's assume that there are all kinds of rules could apply out here, starting from, so all this is free. You don't ever have to do these extensions explicitly. They happen implicitly. The moment you change from phase I to I plus 1, you have remembered last ji, automatically 1 to last ji is done and dusted. You pick up control from last ji plus 1, that is that position. From that point onwards, you're applying rules. Potentially, you would get your rule 3 in this phase, that is rule 3. Okay, if that is rule 3, showstopper, all that gets completely, showstopper implies that once a rule 3, everything is a rule 3, which means that now you have this new position here, which is last ji plus 1. So that was last ji, that was last ji plus 1. What does it mean? It means that everything before pause is either rule 1 or rule 2. We already said that was rule 1. There might be some rule 1s and rule 2s out here. Okay? Now, think about one more iteration of this and you will start seeing what magic this is. So, can everyone see that part of the screen? So that's 1. So that's going to be I plus 1, and there's going to be a new character. Let's call it Y at I plus 2. So this is basically phase I plus 2. I'm linking I plus 1, I plus 2, right? So which means that this was the last J of phase I plus 1. That means that everything before it was either rule 1 or rule 2, which means that in the next phase, all this part would be rule 1, because once it's rule 1 or rule 2 in the previous phase, it's going to be rule 1 in the next phase. Okay? Rule 1 or rule 2 in the previous phase means that it's going to be a rule 1 in the next phase. Now, you are picking up control from here. You might get rule 3 at some position. I mean, the worst case, you never see a rule 3, which means that you've just completely, everything is going to be rule 1. So, can you see, I'm just going to now circle these points. So that's going to be last Ji plus 2. So those 3 bits are always going to be, they have a monotonically increasing numbers. So you can never have this go behind. Okay, there's always going to be at that same point or more. Okay, going forward, you're covering more and more. So that relationship out here is last Ji is less than or equal to last Ji plus 1 is less than or equal to last Ji plus 2. So last ji is less than or equal to last ji plus 1 is less than or equal to last ji plus 2, and so on. Okay? All right, so if that's true, then you're only going to, so in just note one thing, that going from phase I to phase I plus 1, you're picking up the control at the first time you saw rule 3, isn't it? You saw rule 3 in phase I, that's where you start. Is it rule 1, rule 2, rule 3 now with the new letter coming in. Then again, you kind of, first time you saw a rule 3, you stop, go to the next one, you pick up your control again. So between two extensions, between two phases, how many extensions do you repeat? You never repeat before. You only repeat one extension that you did previously. Because if you did pause, you never do anything after that. If you did pause, if you saw rule 3, you never do position minus 1, position plus 1, position plus 2, position plus 3. Those never get done. It's showstopper. You stop the show there in the previous phase. Then you repeat, and then you repeat at that position again in the next phase. So between every two successive phases, you only repeat the place where you saw a rule 3 the previous time. If you didn't see a rule 3 in the previous phase, you never repeat anything. But if you saw rule 3, that extension gets repeated, and see what happens later on. Yeah? All right, no worries. So what this is trying to tell you is that this specific relationship, the monotonicity, okay, after each phase I, the observation from the previous slide that the discussion that we had, that the last ji is less than or equal to last ji plus 1 can be exploited, and we can omit and avoid explicit suffix text extensions. So all this gets omitted. You only start from here, which means that you're only repeating one suffix extension at most one suffix extension, 0 or 1. At most means 0, none, or 1 in every suffix extension. Now, if that were true, then essentially, if all this were true, then if I can convince you that this part where it was rule 1 or rule 2 became rule 1 can be done in constant time, then we have a tremendous promise for a linear time algorithm. We will see what that promise, how we can achieve that. Now, most importantly, when you create a leaf, right? So what would be its a start point and end point? So when you create a leaf, in every phase, what would be, when you do a leaf extension, rule 1 extension, what is endpoint pointing to? Every leaf? Every leaf has to end in if it's a leaf, every suffix that ends in a leaf has to be extended by a character Z, isn't it? So it's always going to be pointing to the phase number. Every leaf will have the endpoint pointing to the phase number. If you were not doing something straightforward, in every phase, whenever you see a leaf, wherever you saw a leaf, the numbers change from I to I plus 1 if it's going from phase I to phase I plus 1. Then if it's going from phase I to I plus 2, I plus 1 changes to I plus 2. The endpoints just get incremented pointing to the phase. So if you then had a trick which whenever you created the phase, whenever you created a leaf, the endpoint is pointing to the phase number. Changing the phase number changes all the endpoints simultaneously. You need a reference. There are many different ways of doing it. One way of doing it, which comes in a way of the algorithm being an online algorithm. Online algorithm is that if you have only partial string, you construct a suffix tree. If you get more of that string, you don't have to start over again. You can continue from that process, but it really doesn't matter. So one trick is that you don't do the endpoint. Whenever you're creating a leaf, so for instance, what would be if I created a start point, end point, the first time the leaf was created? This would be, if it's phase I, minus 1 to I, it would be I comma I, isn't it? It's J, the substring starting at position I, x of one length. That's what I comma I would be. But instead, if I called it I comma n, n is a length of the string. Okay? Although your phase ends at I, you are saying that it doesn't matter whatever the end is, or you could call it global end. Global end. What the global end, one trick of global end is to point it to the length of n, of the string itself. There are many other ways of implementing it. If you call the end as n, then in which case the idea is quite simple. When you go from, whenever you go from phase I to I plus 1, when you see n somewhere, you're interpreting n as whatever the phase number is. Okay? Because I plus 1 is less than n. In the worst case, when you finish the whole phases, I plus 1 becomes n, isn't it? You keep I plus 1, I plus 2, it goes to n. So essentially, you're interpreting, you're just keeping, you're doing a simple trick where whenever you get a new, so for next phase, it's going to be x, isn't it? I plus 1. So going from I to I plus 1, it's going to be, again, a rule 1 extension. So if you had an n there, well, the global end is pointing to whatever the current phase is. The current phase is I plus 1, so I'm still okay. Let's say if you get a y, it's still pointing to I plus 2 now. N is interpreted as whatever the phase is. When you end the process, it's naturally ending in the length of the string. So that's what this trick is. So these are essentially a bunch of tricks. So it's talking about a global end. All you have to do then is to, once you have, if you go from phase I to I plus 1, you don't have to rub the labels of endpoints on every leaf. It automatically gets updated, which means that it's a constant time effort. You don't ever have to go back and do anything here. Okay? Just shift the phase number, rule 1's done. This will take a while for it to dawn on you, but if you did, you will enjoy what a nifty trick this is. Okay? I've explained everything that I had to on this. So we also said that if you did these things, you only have to, everything that we talked about this is giving concrete definition to the intuition I said. Go and read this, it'll cover the intuition of what I have completed. It'll give you some cases where what happens if you never saw a rule 3. If you never saw a rule 3, that means that you have reached the end of a phase without seeing a rule 3, which means that the whole thing is going to be rule 1 now, and changing a phase free. You just have to do an extension with one letter. Okay? No other extensions happen. Okay? And you between two successive phases, you have at most one position, where you would do, so this is the position where you do an explicit, you repeat that process of whether it's a rule 1, rule 2, rule 3. And in which case, if that observation is true, how many phases do we have in Euclidean? If you have a string of length n, you have n phases, and between every two successive phases, you are repeating one suffix extension, so you do at most 2n explicit suffix extensions. Okay? This is not a proof for the linear time yet. I'll come to the next slide before that, but we all said we're interested in a proper suffix tree, not an implicit suffix tree. At the end of the phases, you get an implicit suffix tree. What happens to, how do I get an explicit suffix tree? Easy. Just consider the next phase containing the letter $. So if you want to n followed by a $, isn't it? Do exactly what you are doing as if it's a regular character. Lo and behold, you get all the rule 3s will be, so you essentially get a explicit suffix tree if you extended it with no change to the algorithm. It's the same algorithm, adding one extra letter. Now, I probably will, for the interest of time, I usually give a intuition, in fact, a reasonable proof. I'll probably not make the proof of linear time examinable, but very quickly, I just want to give you, but I'm not going to make this examinable for this semester, so don't worry. But think about it. Everything is not about marks in reality. So we will just take a quick intuition of why. We already said the phase is number of phases, number of extensions across phases is bounded by 2n, because between every successive phase, I plus 1, you repeat one suffix extension, in which case it appears as if that's all there is to proving linear time effort. But the problem is that you still have to do extensions so every time you're doing an extension, each extension could be order n, right? How many letters do you have to traverse? The remainder could be order n. So you could have this complexity that appears as if it's n squared, except that it's not quite. So if you have an active node, this is an active node, let's call this an active node. It points to some v, you traverse, you get another active node in the next extension. So this could be order n, okay, worst case. So if you're doing 2n explicit extensions, and each of them in the worst case is order n, so it's going to be 2n squared, isn't it? But I'm just showing you what really happens. So this will point to some v prime, you traverse, u double prime, v double prime. So this process is essentially covering, so if let's assume that this point was p1 in the string, okay, whenever you're doing the suffix extensions over phases. These are not the label as much as the logical progression of your phases and your suffix extension. If this point was, let's call it P1, okay, or let's call it P, which means that this point would be P prime, this point would be P double prime, and so on, right? I'm just going to point wherever the active nodes are, what is the position with respect to the logical progression with respect to the string. Now, if this was P, do you agree that this has to be P? That's what a suffix link is, isn't it? You're getting a shortcut. So the position where it ends is same as the position out here. That's what we said a suffix link is. So with respect to P prime, with respect to P, what is P prime? Greater, less, equal to. Can P ever be greater than P prime? Because you have to do remainder out here, isn't it? So P is less than or equal to P prime, is less than or equal to P double prime, is less than or equal to P triple prime, and so on. And all of them have to be start at nothing and end at n. Think about how this, and you have to do this in 2n explicit extensions. There are only 2n possible explicit extensions. You start at nothing, you have a distance to cover, you hop. Okay, every time you kind of do something, you've progressed. You're either staying there in the next thing or move forward. Every time you're doing it, you're only covering the distance towards n. The maximum effort has to be, if let's say you traveled a lot in the worst, what we call worst case, you traveled a lot, which means that the subsequent time there's only little for you to travel, because at the end you have to come to the end of your entire string. So you're covering the width monotonically, and the total effort over all possible extensions, total number of effort over all possible extensions is bounded by order n. You don't ever have to go back, and that's because of the what the suffix links are telling you. If that's P, that has to be, then if you traverse the remainder, you get to a P prime that is less than or equal, greater than or equal to P, okay? Then from, if that is P prime, this path has to be P prime, which means then P double prime has to be greater than or equal to P prime. Every time you're going forward and forward and forward, which is the intuition for why this runs in linear time. So with that, I think we have come to the end. There are a few other ways, but I'll not make this examinable because I've just covered the intuition and not proved it solidly. Sorry, wrong. So we are doing our topic. It's okay. We spent quite a bit of a time articulating Euclideans. That's fine. What we can now do is see how much we can cover. There'll be some spillover going into. So if you're not finishing it, don't worry. I'm going to finish it. We'll catch up at some point. But as long as you know that. As long as you know that we're going to cover everything without skimming over any details, that's perfectly fine. So rest assured, don't worry about why aren't the lectures aligned to the logical boundaries, because some lectures can take longer. Okay? We'll catch up in a few weeks, don't worry. If it spillovers, we'll end shortly. Okay, we're doing data compression. I'm just going to I don't have to impress upon you the importance of data compression, really. How many times have you zipped your files and uploaded assignments or sent it to people? It's a common process. I'll just say on that slide, data compression is ubiquitous. You're using it in communication. You're using it to transmit information. It's everywhere, right? And it's there in all kinds of communication that we currently have, and human beings keep generating a lot of data, and that becomes essential. So you know all these formats, zip format, I think that's what you always use, right? So when you compress, now what this lecture will tell you is what is happening inside a zip. Okay, why is it that you can, what is zip is called? I mean, I saw it recently. I think it was called deflating. I think that I usually don't use zip often, but I had to do it recently. So I use some other program equivalent algorithm, but different system. So kind of deflate, compress a file, send it away to any corner of the world. They can recover exactly what you saw, right? They're not recovering something different, are they? That would be a good claim. If your zip program did not have the fidelity to recover, you can say, Arun, you gave me low marks in my assignment because it was meant to be I+1, but it was I encoded it as an I. If you encode it as an I, it would have to be I. It can't be I+1, isn't it? So it is lossless, right? You're not losing any piece of information. Okay, and then compression is the practice of representing information in a compact form. Whenever you want to get something compact, what are the things that you compress? Things that repeat. There's no brainer there. Anything that repeats gets compressed. This is an easy lecture. I think after a tough Euclid, I think this will be fairly easy to follow. Don't worry. So when you have data, you have some redundant, meaning repeating parts, and some parts that are not repeating. I'll call that random, okay? So data can be seen in one view of data can be seen as something that is redundant and something that's not redundant, okay? That is random. You can also say the redundant part is where the compression you get a compression. The non-redundant part is where you don't get compression, okay? You can think about that as in a signal processing way, a signal and a noise, or some model and a deviation. Let's not worry about the later two. It has very interesting implications for a completely different area of research in machine learning. This is very, very important. And you will see when you're doing even the modern deep neural nets, you would see something like information loss. Okay? They're all measuring how much compressibility you're getting out of stuff. So if it doesn't matter in machine learning, information theory, the notion of compression is very important too. and that's where the model and deviation part and signal and noise part comes into the picture. But we're only focused on redundant and non-redundant parts, okay? Now, so natural language, any language you speak, all the common words that things that you say commonly are very short. You don't have a long word for something that describes a category that you keep using, okay? Things that we use often are always short. Things that we rarely use tend to be very long, okay? So frequency of occurrence of something is linked with how small, how compressible, how short or how long a certain statement, a certain messages, right? So you never tend to use words like these. And then there are many things where, like Braille code, Morse code, and other codes for teletypes, they're all age-old information. People have been doing compression for a very long time. The idea of a compression is you have a data, you have some program encoder that takes the data and compresses it. That's the encoded data in red. And you have a program that decompresses the encoded data. When you send me a zip file, I have a program that does the opposite of compression, that uncompresses it, and I recover the data. And that process of getting the data exactly as you have encoded it is lossless data compression. Any doubts so far? Nothing major? Anybody? Any questions so far? Okay. So in which case, you all know what fixed length codes are, and in fact your understanding of learning of what computer science is will improve if you understood a generalization of this. So fixed length codes are codes because you all store in bits on a computer, okay? So every letter has the same number of bits to represent it, okay? ASCII codes are 7-bit or 8-bit extended ASCII. Every single letter coded from 0 to 255 is mapping onto some letter. So if you have capital A, it maps to number 65, but number 65 is stored in 7 or 8 bits depending on if it's a standard ASCII or extended ASCII, okay? And if you have understand what I mean? So fixed length codes are codes that take same number of bits to state. If you have same number of bits to state, irrespective of how often it appears, then it has an advantage of not being, there's nothing that you have to do, just read 8 bits if it's an 8-bit code and say which number is it, then it's number 65, oh then they meant A. It's easy to recover, encode and decode. But then problem is that it is not efficient because you're storing, even if it's number 1, it only requires 1 bit, let's say, and you're still storing 8 bits for something that is common or something that is frequent, gets the same number of bits as something that's infrequent. Okay? So this is an 8-bit ASCII code. So decimal 0, 1, 2, 3, 4, 5, 6, all the way to 127. So 7-bit code is what I'm showing here. Binary and octal, hexadecimal, and the symbols. So if you can see, capital A would be 65. Okay, small a would be 97, I think, 65 plus 32. Yeah, the 97. Okay, so it's basically designed in a way which is makes encoding and decoding the transfer of information easy. So the new thing that you will learn in this lecture is variable length encoding. Okay, that means that some of them take fewer number of bits to state, some of them take more number of bits to state. And your compression algorithm is nothing but a combination of variable length encoding on things like a single letter, integers, or strings of letters. Essentially, all the underlying algorithm is doing is, it is whenever you need an integer, and we'll see why you would need an integer once we traverse this lecture, maybe in the next first half of next lecture, we'll see why you need, why we would actually need an integer encoding. How do we encode integers? So variable length encoding integers. Fixed length is easy, right? 65, or change it into, so all your computing assumes, so when you say integer, you don't, although Python hides the detail, I think Python integer class is a big int class. But in principle, you think as if it's a 32-bit or 64-bit number. But integers can be arbitrarily long. They are countably infinite integers. And if you say that my range is not 32 bits, okay, if my range is not 32 bits, in 32 bits, you can only store numbers from 0 to 2 to the power of 32 minus 1, 4 billion-ish, okay? 16 bits, you can only store from 0 to 65535, yeah? 64,000. But as the number increases, you need more and more, okay? So how do you come up with a variable length encoding scheme that allows you to, so compression uses variable length encoding scheme for characters, for substrings, strings. How do you encode variable length encoding using for substrings? We'll see how that works, and then for integers. And if you had the variable length encoding scheme for this, for those ingredients, those atomic things, then you can write a compression algorithm that's pretty close to what zip does, okay? The only detail is how fancy the data structures are, but the core algorithm would be the same. In fact, what we'll be learning, Lempel-Ziv 77, is an algorithm that's used in zip, okay? So, and it's a very easy algorithm. It's not at all tough. Perhaps the easiest you will find in this unit. Only have to wrap your head in your of how to get these done. Okay, so just to give you a sense of what a variable length code is, you know Morse code. I think some of you would have heard about Morse code during most of the communication during the World War happened, or at least in the last last century primarily happened in Morse, or at least it arose a little earlier. I think it arose in late 19th century and got used in at least the first part of 20th century. So you have dots and dashes, the sort of a binary system, dot and dash. So whenever you see a big line, it's a dash, it's in dots. So A would be dot dash, B would be dash dot dot dot. So if you look at this as a tree, when you go left, it is a dot. When you go right, it's a dash. So if you look at the code A, so dot go left, dash go right, that's an A. Okay? And then B is dash dot dot, so go right, left, left. Right, left, 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 the 3 dots, that's B, and so on. Okay? So that's a variable length code. Can you see that some letters are smaller, and why did they have to create these two? The system of variable length is because if you're transmitting a message with letters, the frequent letters have to be short. Otherwise, you'd be, if you had long strings for frequent letters, then the communication would be longer, isn't it? Intuitive. All this is context. It's not really. So the idea would be that if you have something that is very frequent, that needs to have a shorter code. Something that is infrequent would have a longer code. So things like ZQX hopefully would. So if you look at things like ZQ, can you see that they are sort of longer codes? I mean, the dash had a certain latency to it as well. So we'll not go into this is not meant to be an exact representation of frequencies, but it captured the idea of things that are frequent are smaller and things that are not frequent are longer. Okay? Now, with that background, we'll see, what's the time? Give me a second. Yeah, I think we can cover some part of it, don't worry. So what's the problem with variable length code? Now, take integers, right? Integers, if I said, why are we storing integers as fixed length? We can store them as variable length just based on their binary strings. If it's 0, you store 0 bit. If it's 1, you store 1. If you store 2, 1 0, 3 1 1, 4 1 0 0, 5 1 0 1. Yeah, you get the point? What's the problem with that? Anybody? You can't use that for compression.
So an example would be, say if you're trying to save 20 as in 2 and 0, right? So it would be 1 0 0, right?
No, if you're saying 12, let's say 12. Was 12 the number you said?
No, 20.
20. So 20 is 16 plus 4. So 1 1 0 0 would be 20.
No, I'm thinking in like a concatenation term. So if you're just like, if you have a 2 and 0 next to each other.
Okay, it's okay.
So that would be stored as 1 0 0, right?
Mm-hmm.
But once you're decoding it, you see it as 1 0 0, which should also be 8, and you don't know which one.
Okay, I think you hit the nail on the head. I'll try and rephrase what you just said in a slightly different way. What if you were not sending one integer, but you're sending multiple integers at the same time? Let's say I have sending 25 as one integer, followed by, so 20 as one integer, followed by 12. So 20 would be 1 1 0 0, and 12 would be 1 8 plus 4. So 1 1 0. Yeah, I think. So 20. So it would be 5 bits, isn't it? So 1 1 0 0 0 would be 20, and 1 1 0 0 would be 12. I think that's what I would have. You know, 20 would be 1 1 0 0 0. 0th place, first place, second place. Third place and fourth place would basically be. I'm sorry, 16 plus 4, isn't it? 1 0 1 0 0 is 20. Early in the morning, sorry, 20 would be 1 0 1 0 0, and 8 would be 1 1 0 0. Okay, and 12. So if you had those two numbers next to each other, so let's actually write them. So I should have. So 20 in base 10 would be nothing but 1 0 1 0. So that's going to be 16, 8, 4. So that's going to be base 2, isn't it? And then 8, so let's call it 12. 12 base 10 would be nothing but 1, 1, 0, 0, base 2, right? So if I sent numbers 20 and 10 in one message, I would basically have numbers like 1, 0, 1, 0, 0, 1, 1, 0, 0, because they are variable length, right? Now previously you could recover 20 and 12 because they were all 8 bits long. So you read 8 bits. What is the number in the 8 bits? It's 20. With lots of zeros padded in the most significant thing. But now when you have it, well, is it a bunch of those many numbers? Or is it a bunch of numbers of different sizes? So you could have many ways in which you could decode it. Okay? Ambiguous ways in which you can decode it. So problem with variable length encoding is that if you had a code associated, you can generalize this idea not just for integers but for any letters, for instance. If you had A coded with 0, B coded with 1, C coded with 1 0, and D coded with 1 0 1, let's assume, and you send BA, the code under this this code book, the book of codes, is 1010, right? That's what you would code. But when I have to decode it, I can decode it as 1010, each of them being BA, but I can also decode it as 10 space 10, which is going to be CC, or I could decode it as 101 space 0, which means DA, right? Which means the space is trying to tell you that that's not a real space, but it's the logical way in which you're splitting that word, which means that I don't know, my goal is for it to be lossless, right? Your zip shouldn't give me this output if you encoded something into a file, correct? So now, if I did this code instead, that is decodable uniquely. Can you tell me why? Just a moment, let everyone think, and I'll come back to you. Yeah. So if I encoded 0 for A and 10 for B, 110 for C, and D is 111, encoding BA would give me 100. That's going to be uniquely decodable. There's no other way that you could decode it. Yes, sir. Why would it be?
So the shorter code words can't be prefixes of long words.
Fantastic. The shorter code words are not prefixes of longer code words. Now, is 0 prefix of any other code? Is 10 prefix of any other code? Is 110 a prefix of any other code? So they are prefix-free codes. Okay, code that is prefix-free. They're sometimes called prefix codes for some reason, but really they're prefix-free codes. So essentially, no code word is a prefix of the code words, so they're called prefix-free codes. Sometimes they drop the free, they're called prefix codes or instantaneous codes. So that's what we want. When you talk about variable length encoding, somehow I have to, for this example on the board, I have to come up with a way in which I can convert letters into prefix-free codes and numbers, integers into a prefix-free code and so on. Does that make sense, the idea of what we are trying to do? Okay, so if that's there, I'm going to, the agenda over, so we are kind of close to, we got about 15 minutes before we wrap up. I'm going to use all this time, at least finish Huffman code. And then the next lecture, I'll talk about, so we need a code, a variable length prefix-free code for characters. That's the first thing we're going to do. Then going to do in the next lecture, start of the next lecture, variable length prefix-free codes for integers. Now, once you have those two things, we're going to then go ahead and use them for a compression. Okay, that's the agenda. So these are like the spanners and nuts and bolts for a compression algorithm. So what we're learning is how do we do first the prefix-free code for characters, single characters. You have an alphabet, how do you come up with a prefix-free code? The codes basically we're going to learn is an easy one called Huffman coding or codes. Huffman was a third-year undergrad student when somebody post him, Kolmogorov, in his class post a challenge that you couldn't possibly beat the code that they had. Well, you could do better than that. And then he went ahead and maybe overnight slogged it out and came up with a code which had extraordinarily good properties theoretically and practically, gets used all the time. Okay? So it's a practical algorithm which has, it's like a tip of an iceberg, the practical part. The theoretical properties of this are far more fascinating too. If you're doing a proper course in information theory, we would have gone through some aspects of this. Okay, the algorithm ensures that the lengths of the code that you want to get a prefix-free code, but you also have to say that if something is frequent, I want my code to be small, but something that's infrequent, it can be large. Okay? So you want all the frequent ones. Why do I care about frequency being small? Because if it's frequent, that means my entire coding of a collection of characters with a certain distribution of characters would be small. That's the whole idea of compression, isn't it? I want it to be as small as possible and recoverable. And the algorithm is so easy, it's a greedy algorithm. You could get through this algorithm quite simply, and as you can see. So here's an example I've taken from Wikipedia. I like this example because it's all colored, and I couldn't be bothered coloring it on a different example, so it's easy when it's there. It's a reference. If you click on Wikipedia, it'll take you. That's a clickable link, hyperref. Okay, here's a certain string. Okay, the colors tell you the different characters, right? There are a bunch of characters. Instead of a space, I used an underscore. That's all. Okay, and I claim that there are 2 C's, 6 B's, 7 E's, and so on. Okay, can you just eyeball and say that's reasonable? I mean, no reason Wikipedia would have got wrong with those counts. Yeah, you can see there are 2 reds, for instance, right? And 6 purples or violets, whatever you want to call them, and so on. Now, if you see, those letters are arranged in a specific order. The most infrequent at the top, the most frequent at the bottom, right? Sorted in the order of their occurrences. Everyone clear? Algorithm works like this. Take the 2 infrequent symbols in my current table. So what's the 2 infrequent symbols here? C and B, isn't it? Group them, call it a special symbol called CB. Okay? So think of that to be a set, CB. Okay? So it's an internal node, and if I go to the left of that internal node, it's a binary, I'm creating a binary tree. If I go to the left of the internal node, I'm going to call that to be the smaller of the 2. The 2 that are 2 infrequent, C and B, appears 2 times and 6 times respectively. Left is the smaller of the 2, right is the greater of the 2. Okay? If they are both equal, it doesn't matter which order you want to put it. Okay? So if you can create a binary tree, CB, now together C appears twice and B appears 6 times. So together that set CB appears 8 times, 2 plus 6. Yeah? To the left is C, to the right is B, going left is 0, going right is 1. Okay? Now I have reduced this entire set by, so I've replaced C or B by one set CB. Now I can put that special symbol CB into my, so look here, if I put my CB, so I've removed CB, C and B independently, now it appears together as a special symbol. Previously they were 2 and 6, so 2 plus 6 is 8, so they get pushed into its place, isn't it? Repeat the process, rinse and repeat. Find the 2 most infrequent symbols in my table. Well, it is E, which is 7, and the previous combined symbol CB, which is 8. So now I have a set ECB. The total count would be 7 plus 8, which is 15. Now E was smaller of the 2, so one was 7, one was 8. So go left is E, go right would be CB, but CB was already a tree, so this tree repeats here, right? Can you see that? Now repeat the process, insert ECB into this list, so the ECB gets inserted in its right place. So can you see that it gets inserted? 15 means that it's going to be most frequent together, ECB together is most frequent. Repeat the process, take the 2 infrequent ones, combine, left would be the smallest of the 2, right would be greater than the 2. Can you see that both were 10? It really doesn't matter which direction it would have gone. You could have swapped the order, it doesn't matter. Okay? It would give you a slightly different code, but it really doesn't matter for the algorithm. Okay? You're doing a greedy choice. Always the 2 infrequent, and if they're same, any one of the 2 could be left and the other would be the right. So going left is always treated as 0, going right is always treated as 1. So now 10 plus 10 is 20, put it back into its place. So that now you have those 3, take the 2 infrequent, 11 plus 15 is 26, Left is the smaller of the two, right is the greater of the two. Okay, so ECB is 15, but ECB is nothing but that tree, the tree out here. Okay, whatever tree you see here is the same tree that you're seeing here. And then you repeat the process. So, AECB goes to its place, so that's going to be down at the bottom of this place, and that gets collapsed, right? So those two get collapsed into AECB, and that goes right there. So what's remaining are those two. And when you complete this process, every time you're decreasing it, can you see that you end up getting a rooted tree, a binary tree with zeros and ones? That's all you would get. In which case, can you look at what's on the leaves? Is the leaves always a symbol? Okay, is a leaf of the tree always a symbol? And internal nodes are always combinations of them as you're going up. At the root will be all combination of all leaves. One way down, it's combination of whatever the subtree, leaves at the subtree are, right? In which case, is that a prefix-free code? Why? What is the code here? Okay, what's the code for C? Well, traverse the subtree, go to the root, right, left is E. So 1, 1, 0 is your code for E. If you want to code for B, right, 1, 1, 1, 1 is basically the code for B. Code for D would be left, right, 0, 1. Yeah, can you see that? So the code for space or underscore is left, 0, 0. Can any two codes be prefixes of each other? Why? Because the codes are at the leaf, and two leaves are never, a leaf by definition is split off an internal node, right? So they can only share a prefix up to an internal node before they differentiate. So you never have two leaves, codes at two leaves. So in which case, I could have encoded this entire string much more. So my code would be underscore is 0, 0, D is 0, 1, A is 1, 0, E is 1, 1, 0, C is 1, 1, 1, 0, and so on, right? B is 1, 1, 1, 1, 1. I could have encoded all these things instead of having ASCII characters, 8 bits per letter. I now have, every time I see it, I can encode my string of characters like that. And those colors tell you which code it represents, right? Now, obviously, bits are not colored, right? When you have to decode it. Is decoding easy? How do you decode? If all you had was this without colors, how would you decode? Okay, let's start here. Let's start at that 1. Okay? So we don't know what code it represents, right? So you're starting at the head of this tree, this Huffman tree out here. So when you start this algorithm, when you start decoding it, you are out here at the root. You saw a 1. 1 means go right or go left in the scheme. Go right, isn't it? Go right. Did I commit a leaf yet? No. What's the next bit? 0. Okay, first bit was 1, second bit was 0, right? 0 means go left. Is that a leaf? Yes. I've spit out a symbol. What's the symbol there? That's A. That's the first letter here. Okay? So then my pointer reading the bits would be that where, go back to the start of the tree. Once you spit out a letter, you go back to the start of the tree. Okay? So that is 0, left, 0, left, it's a space, spit out a symbol, underscore space. Now I'm going to point my position there. 0, 1, left, right. So every time you're asking, every time you're reading, when you spit out a symbol, you're at the root, and you're descending the root every bit, and every time you're descended a thing, you're asking, is it a leaf? If the answer is a leaf, well, spit out the symbol and restart your traversal. Can you see that this traversal is trivial? Okay, so that's what decoding is, right? So Huffman algorithm is basically a simple algorithm. I'm sure you would be able to code this 2 years ago, okay? It was easy enough for you to do that. But you will see that this is not what zip is doing in terms of compression, okay? If that's all there is to it, then compression algorithms are simple. But what compression algorithm is trying to do is not just see if a letter could be shortened in the code, it's also saying what is the redundancy in your text. If there are patterns that repeat, substrings have to get compressed. If let's say that you saw, take for example, real world example, genomes, right? Human genomes, every time you go and get yourself sequenced, you have a copy of your genome, 3.2 billion letters in a certain alphabet. Now, 2 human genomes have, each of them have 3.2 billion letters, but there's a lot of commonality between them. So if I have to store them, I don't need if I'm using a 1 byte code, so 8-bit code, 3.2 billion would be roughly 4 gigabytes, right? 3.2 gigabytes. Billion means giga, yeah? So you can see that it takes, and every time I need another genome, so another 3.2, except that there's about 99% similarity between 2 genomes, so you only get, the first time you represent something, it takes 3.2, the next one is going to be delta, and delta, and delta. It's a very small difference between the two, so you get, instead of having a lot of space, so Huffman coding is only as an atomic operation, it's giving you the spanner for you to build a higher order compression scheme, okay? So it's not a compression scheme yet, although it can give you some compression. Now, decoding is simple, we already said why. Very quickly, now I've told you how to shorten and encode prefix-free characters. If I then get the other remaining spanner that you need for building a compression algorithm, how do you do for integers? So integers, you cannot use Huffman coding. Why? I mean, I'll just give you the intuition and then we can pick it up from the start. Why can't we do Huffman coding for integers? Yes, exactly. Great point. So if you, the space in which you are mapping these things can be arbitrarily wrong, right? I mean, although there is a natural tendency that we always consider integers that are small, there's no reason. Any code should be able to deal with any circumstance, any integer that could come to you. It could be a large number. So if somebody wants to store ginormous numbers efficiently, a string of them, they should be able to, theoretically there has to be a scheme, even if practically you only might use the first trillion maybe in all day-to-day bread and butter activities, you still need a scheme that can handle any integers. In fact, they're countably infinite integers, right? So they map to a countable set. It's called a countable. Countable doesn't mean that it is, so you can have countable implies that you're mapping anything into a thing that you can count. 1, 2, 3, 4, 5, 6, and that count can go to infinity. That's why they're called countable set. Real numbers are not countable. Okay, so you can. There's a big story about how Georg Cantor was ridiculed in his. He's a famous mathematician who was ridiculed for coming up with the notion of countable denumerable infinities and non-denumerable infinities. Set of integers are mapped to the set of countable infinities. Set of real numbers mapped to non-denumerable, non-countable infinities. For instance, rational numbers, numbers that can be written, real numbers that can be written as P over Q, they are countable. Okay? The rational numbers are countable. Why is it countable? It's because you can have a scheme that says 1 over 2, 1 over 3, 1 over 4, 1 over 5, then 2 over 3, 2 over 4, 2 over 5. You can say that's 1, that's 2, 3, 4. You can map an integer onto a rational set of rational numbers, so that's a countable infinity. but then, and the number of things that are in between those rational numbers are irrational numbers, right? That they cannot be expressed as P or Q. They are a kind of infinity that bizarrely bigger than the countable set. In fact, the probability of picking a rational number between a range is 0. There are so many more of uncountable. So we don't have to worry about real numbers for the moment. We're going to talk about integers. So how do we essentially deal with it? So what we're going to do next lecture is talk about a beautiful code that allows you to do that. I think we'll stop here. It's a natural place to stop. Please go through the slides coming into it. Also, this week you will have Euclid to think about and your deadline. You have a deadline for your assignment. I'm going to have 3 consultations for this week. So Tuesday, Wednesday, and Friday. Is that correct? Yeah, Tuesday, Wednesday, and Friday. The information would be on the forum and the Moodle. Yeah, the Wednesday one is a special one.